Okay, so when we last left off, we discussed the Sn2 reaction. Now it's time for us to talk a little bit about some added sort of quirks of the Sn2 reaction and some interesting cases when we start to observe intramolecular reactions or reactions where there is an internal nucleophile present in our molecule. So, nucleophilic substituents such as halogens, to a lesser extent, and mainly carboxylic acid, alcohols, amides, and amines can react via intramolecular Sn2 reactions. Now, this is important to keep in mind because these intramolecular reactions are generally quite fast, as the nucleophile and electrophilic carbon are held in close proximity. So, for example, we have our internal nucleophile, and we have our electrophilic carbon. And so we can observe a very fast and efficient intramolecular Sn2 reaction. As we notice, we still observe inversion of stereochemistry. We can prove this to ourselves by noting that this first center is an S stereocenter, while in the product, if we redraw it in an alternative way, if we wanted to redraw the product to make it easier to see, we notice that the center is now R. So this reaction is very, very fast because rather than having to wait for both of your reactant molecules to collide, you've tethered your nucleophile and electrophilic carbon in very close proximity, and as a result, you observe a very, very fast rate of reaction. If you try to do kinetic studies on these kinds of intramolecular reactions, you wouldn't see the typical pattern for an Sn2 reaction because by definition, there's only one reactant molecule. Nonetheless, you still see the same solvent effects and you still see the same condition effects on the rate of reaction. But in general, these kinds of intramolecular reactions are very fast. Does that idea make sense to everyone? Okay, perfect. So by the same token, if we start off with the following stereochemistry, we can observe an intramolecular reaction and we observe inversion of our stereocenter. So in this case, we clearly see that we are starting with an S. Let me just check this really quickly. So we're starting with an S stereocenter, and then in our product, we end up with an R stereochemistry. Always make sure for an Sn2 reaction that you're checking for proper inversion of stereochemistry. The other thing that I'd like you to note when visualizing these intramolecular reactions, is that you want to make sure that your nucleophile is appropriately lined up, for displacement. So do we notice in both of these reactions, the way that this chair conformation is drawn for this intramolecular reaction, that we have our nucleophile directly attacking opposite to our leaving group? Does everyone see that our nucleophile is set up exactly opposite to our leaving group? So it's important to appreciate this geometric constraint for the Sn2 reaction. Remember, the nucleophile always attacks opposite to our leaving group. So as a result, generally you'll see that the reactive conformation sets up our nucleophile opposite to our leaving group. So these are two ways of visualizing the Sn2 reaction from an intramolecular sense. So whichever method is easier for you to process and whichever method is easier for you to interpret, that's the method that you can use. So we've seen some intermolecular reactions. So let's take a moment and let's try to predict the product from the following reaction. And I'd like us to try to utilize the annotate tool. And your main check is just to make sure that your target stereocenter for the Sn2 reaction actually undergoes a change in configuration. So let's take about 2 to 3 minutes and let's try to draw a mechanism and predict the product from the following reaction. And don't be shy to share your responses using the annotate tool, or you can share your questions in the chat or verbally. Would anyone like to try to annotate a proposed mechanism or proposed structure for the product? Let's keep working through this example. You can even post your proposed mechanism in the chat as a picture, but I'd like to make sure everyone's comfortable with the general arrow pushing mechanism for the Sn2 reaction and drawing out the products with the correct stereochemistry. Remember, the Sn2 reaction occurs with inversion of stereochemistry. So would anyone like to propose a mechanism or propose a structure for the product from this reaction? Or does anyone have a question on this example? Let's try to get a few responses before we discuss this example as a class. This is a reasonable framework for a question that you may see on an exam, in that it requires you to not only draw a mechanism, but predict the products from the reaction. Does anyone have an idea? And just as a reminder, you can use the annotate tool under the meeting options feature. Would anyone like to share the mechanism that they've come up with, or would anyone like to share the product? So we have someone mentioning, okay. So we have someone mentioning in the chat, the nitrogen will attack. The iodine is displaced, and in our product, so in our product, they indicate that the ethyl is dashed. Okay, so let's take a look at this. Let's assess this and let's try to figure out what's going on here. So first and foremost, we have an R stereocenter. And in the product, let me just check to make sure that the product, so we have priority 1, 2, so that shouldn't have the ethyl drawn with a dash. It should be like this. Of course, there are ways to rotate this molecule. I'm just drawing it focusing on the nucleophile being the position on our stereocenter that gets the wedge or dash. I just find that's easier because if you start with your leaving group dash, your nucleophile will attack on the opposite side and it will end up wedge. So checking just to make sure that we have inversion of stereochemistry. We have our S stereocenter, perfect. So now that we have that all set up, now that we have verified that this reaction occurs with inversion of stereochemistry, we can draw and just redraw our final product. So this is our expected product from this Sn2 displacement. Does that idea make sense to everyone? So a few things to keep in mind. The Sn2 reaction occurs with inversion of stereochemistry, and it is a concerted attack of our nucleophile followed by loss of our leaving group. So to draw out the intermediate steps after our first attack, now that we've clarified our stereochemistry, we have this following protonated amine after cyclization. Now, typically we're not going to isolate this salt. Instead, what we're going to do is, under the reaction conditions, we're typically going to observe a deprotonation event. So after we've generated the cyclic species and we've verified the stereochemistry is correct, we're going to deprotonate our amine to generate our final desired product. So the way that I like to tackle these problems is first I make sure I have my stereochemical outcomes sorted, and then I check and I make sure that I've accounted for any intermediate steps in the mechanism. So we have our cyclization, we make a cationic species, we have a base floating around, so we can pull off a proton from that base and generate our neutral amine. Does this example make sense to everyone? Does this example make sense? Any questions on this example? Okay. So let's talk next about genuine anchiomeric assistance, which is best called neighboring group participation. So nucleophilic substituents such as halogens, carboxylic acid, alcohols, amides, and amines can react via intramolecular Sn2 reaction. Now, it's important to appreciate that the substituents must be trans or have the correct geometry for Sn2 attack. Additionally, the molecule must be in the correct conformation for the desired Sn2 reaction. So, I'd like you to pay attention to this stereocenter for a moment and think about what happens when we treat this molecule, when we treat this substrate with sodium acetate. Now, we would expect, so what stereochemistry would we expect? If we start with a dashed chlorine and we have an Sn2 reaction with the nucleophile acetate, would we expect, what product would we expect? What would we expect for our stereochemistry for the newly installed acetate substituent? Would we expect it to be dash or wedge using our model of the Sn2 reaction? What would we expect intuitively? If the Sn2 reaction occurs with inversion of stereochemistry, we would expect a wedge, right? But what we observe and what is observed almost entirely is a dashed stereochemistry. Now that's weird, right? So when you see these kinds of unexpected examples where we're clearly operating through an Sn2 mechanism, we have a reasonably strong nucleophile and we have a polar aprotic solvent, it's important to think a little bit for a moment and consider this idea of anchiomeric assistance. Okay, so we have a result that contradicts our expectations. What's really happening in this process is we have two Sn2 reactions occurring, or a quote unquote double inversion. Okay, so let's take a look at our substrate here. So wedge dash, so up and down. Do you notice how both of our substituents are nucleophile internally and our leaving group are trans to each other? Does everyone see this trans relationship? It's really easy to see if you draw out a chair conformation. So these two structures are the same. And do you notice in the chair conformation that both of our substituents are trans? Does everyone see that first part? How both of our substituents, one of our substituents are down, the other substituent is up. Can I get some confirmation in the chat that everyone sees that first idea? Can I get some confirmation in the chat that everyone sees that first premise? Now, let's make a model of this because it's really important to view a model to begin to understand trends and patterns when it comes to anchiomeric assistance and anchiomeric effects. So I'd like you at this time to break out your model kit and start putting together a model for this structure. And don't worry, you can follow along with me in the video as well. But I find it's often more intuitive to see if you generate your own model kit. And that way you're developing that skill so you can apply it on an exam. Okay, so let me get this confirmation all set up and ready to go. Okay, now let's open up the camera and let me just get this set up. Whoops. Okay, let me resize this screen just so that way we're able to see this fully. Okay, that's a little, okay, perfect. Okay, so can everyone see the following? Can everyone see the following model? Can everyone see the following model for this structure? Can everyone see my model kit? And let me just adjust it so. One moment. Let me adjust it so that way it's visible to the camera with the correct view. Okay, so here's our view of this structure. So here's our view of this structure. So first thing to note to keep in mind here, do we notice how both of our substituents are equatorial? Does everyone see how both of our substituents are equatorial? Okay, now, are we set up for an intramolecular reaction? Is our nucleophile set up to attack the back of our electrophilic carbon? Is this geometrically set up and ready to go? Is this geometrically set up and ready to go? Do we have the right geometry? No, we don't. However, after a chair flip, let's show our chair flip now. So after a chair flip, we notice after a chair flip, now do we have our nucleophile and leaving group set up in the right geometry? Do we have the right relative geometry for an intramolecular reaction? Is our nucleophile set up anti to our leaving group? Yes. So then we can see an intramolecular reaction where we kick out our leaving group. So there's a really important idea here. We have a ring flip, and that gives us our reactive conformation. We then see our first intramolecular Sn2 reaction. So this intermediate, so just to assign stereochemistry, are both of these oxygen substituents pointing up or down? So if we had to draw a dash wedge depiction of this, are both of our oxygen substituents pointing up or down? Up, exactly. So this is our intermediate from the first step. Does that make sense to everyone? Okay, so we have our first intermolecular Sn2 reaction, and we get the following intermediate. Okay, now that we have the following intermediate, we can then open up our cyclic epoxide intermediate with our nucleophile. And so in this process, we can observe a second Sn2 reaction. Now, let's think a little bit for a moment about how will our nucleophile open up this cyclic intermediate. Okay, my question to all of you is, which carbon is more reactive? Which carbon is more reactive? We have a choice here. We have a tertiary carbon and a secondary carbon. And which carbon is preferred for the attack for an Sn2 reaction? So in general, the Sn2 reaction is very sensitive towards the substitution of your carbon containing your leaving group, right? And we discussed previously for an Sn2 reaction that primary substituents react way faster than secondary, which react way faster than tertiary. So with that pattern of reactivity in mind, would we attack at the tertiary or the secondary carbon? We'd attack at the secondary carbon, right? So we'd open up our cyclic epoxide intermediate by attacking our secondary carbon. And that would look something like this. So we have our second Sn2 reaction. So if we wanted to see this in dash wedge notation, we'd have the following epoxide intermediate, and acetate would attack our secondary carbon and open it up. And as we see now, we have a chair conformation where both our oxygen from our epoxide and our nucleophile are trans or anti to each other. And this occurs because the Sn2 reaction occurs with inversion of stereochemistry. So in the end, we have the following intermediate, which matches this chair conformation depiction. Does this idea make sense to everyone? Does everyone notice how the presence of an internal nucleophile leads to this quote unquote double inversion? Does that idea make sense? Can I get some confirmation in the chat that everyone understands that idea? It's just two Sn2 reactions occurring one after another. Okay, now this is where things get really interesting. Anchiomeric assistance is also observed for acyclic systems. So you have the following alkyl iodide and you treat it with sodium bromide. We would expect intuitively that we would just have attack of our bromide and we'd end up with our product giving inversion of stereochemistry, right? That's what we would expect as sort of the natural outcome of this reaction with no other external factors. However, as we clearly can see, do we observe inversion of stereochemistry? Do we observe inversion of stereochemistry? No. So anytime you observe retention, I want you to think and be on the lookout for this idea of double inversion. Now, this is super common when you're looking at like sugar chemistry or in other molecules where you have a load of internal nucleophiles that can potentially participate and engage in the reaction and as a result transmit some stereochemical information. So is this thiol, would we consider this thiol a reasonable nucleophile? Is this thiol a nucleophile, electrophile? What is it? What do we think about it? If you think about our list of nucleophiles, yeah, this thiol functions as a perfectly good nucleophile. So it can attack, and we can observe our first Sn2 reaction. Notice that we have inverted this stereocenter in our first Sn2 reaction, right? Does everyone see how the stereochemistry has changed on that stereocenter? Does everyone see how we went from an S stereocenter to an R stereocenter? Okay, so that's our first Sn2. And now that we have bromide floating around, it can open up this sulfur-centered epoxide in a second Sn2 reaction. So in effect, we observe retention of stereochemistry via double inversion. This is a hallmark of anchiomeric assistance. And the really interesting thing about anchiomeric assistance is that the moment you get to this cyclic intermediate, this cyclic intermediate has in effect translated or transferred some of the stereochemical information from this adjacent stereocenter into our reacting stereocenter. So this is sort of building the stage for broader ideas of stereochemical control via adjacent group participation. Anyway, this is a very common trick question. You'll see this a ton, not only this semester, but next semester. And it's pretty relevant in biological systems when you start to deal with sugar chemistry, as you essentially have 5 or 6 protected or unprotected adjacent groups ready to go that can engage in anchiomeric assistance. Does this idea make sense to everyone? When you break it down, it's really just multiple Sn2 reactions, one intramolecular, then the second intermolecular. Okay, so let's test what we've learned here. And I'd like us to predict the product of the following reaction, and I'd like us to draw a mechanism for this reaction. So in this case, we have an acetate moiety. This is a big offender when it comes to anchiomeric assistance. And I'd like you to tell me, what are the products from this reaction? Now, just to keep our ideas from spiraling in too many different directions, let's just focus bare bones here. What is our nucleophile and what is our reactive carbon? What is our nucleophile and where is our reactive carbon? So let's start with the nucleophile. What's the nucleophile in this process? What is our nucleophile? Yes, that's one of our nucleophiles, yes. But what is our reagent nucleophile? What is our external nucleophile? So CH3CN is our solvent. What is our nucleophile? So we've added sodium iodide sodium iodide in acetonitrile. What is our nucleophile in sodium iodide? What is our nucleophilic species in sodium iodide? Yeah, iodide, exactly right. So our nucleophile is iodide, okay? And let's just label these carbon A and carbon B. Which of these carbons is most reactive in an Sn2 reaction? Which of these carbons has the better leaving group and is the least substituted? A, right? Okay, so perfect. So we've identified our reactive carbon and we've identified our nucleophile. Okay, now what I want us to do is I'd like us to use the annotate tool to try to draw a mechanism for this reaction. You can even share a picture of the mechanism for this reaction in the chat. And then I'd like you to predict the product from this reaction. And I'd like to see some drawings for the product from this chemical reaction. So let's work on this example over the next few minutes. And let's try to get the proposed responses in the chat or verbally. So what is everyone thinking so far? Would anyone like to share their proposed response? Would anyone like to share their proposed response or proposed mechanism? So we have a combination of an internal nucleophile and an external nucleophile. Would anyone like to comment on the product generated from this reaction? So let's try to get some shared responses for the mechanism for this reaction. And we'll discuss this example in about another 1.5 to 2 minutes. Okay, so we're definitely expecting some sort of Sn2 displacement on stereocenter A. And just to make sure everyone's been paying attention, for the stereocenter attached to our iodine atom, would we expect a dash or a wedge? Would we expect a dash or a wedge? Now this really gets to the heart of this problem here. Would we expect a dash or wedge stereochemistry for the iodine? for this exact reaction in particular, if you ran this reaction, what would you expect for the product? Keeping in mind all the external factors. What does everyone think? Do we expect a wedge or a dash for our product? Accounting for anchiomeric effects and accounting for assistance effects. What does everyone think? Would we expect a wedge or a dash? So I have a lot of students commenting that they would expect that the product would have the dashed stereochemistry, and that is exactly correct. But let's talk a little bit about why that is. You have to be able to rationalize your responses clearly using a mechanism and the pattern observed for reactivity. So first and foremost, we have an internal nucleophile. So we're going to observe an intramolecular Sn2 reaction. That in turn gives us the following cyclic intermediate. Okay, now, do you notice how in our first intramolecular Sn2 reaction, we have inversion of stereochemistry? Now, our nucleophile, our external nucleophile is able to react because the intermolecular reaction is a little slower, so the external nucleophile reacts second. Now, labeling my carbons A and B, where will my nucleophile attack? Where will my nucleophile attack? A, right? The secondary position is more reactive than the tertiary position. Okay, and that in turn gives us as our final product so again, this is a classic case of anchiomeric assistance or neighboring group participation leading to a quote unquote double inversion of stereochemistry. Does this example make sense to everyone? Perfect. Okay, so let's keep going now. And let's introduce our next major type of reaction, which is the Sn1 reaction. So Sn1, substitution, nucleophilic, unimolecular. Okay, so mechanistically, the Sn1 functions where the rate limiting step is unimolecular, And we'll see as we look in detail into this mechanism, the main distinction between the Sn1 and Sn2 reaction. So let's start off by looking at the reaction of tertiary alkyl halides. Tertiary alkyl halides react rapidly in protic solvents by a mechanism that involves departure of the leaving group prior to nucleophilic addition. So this is a two-step process. Okay, so the Sn1 reaction occurs in two distinct steps, with the rate limiting step being unimolecular. That's what the 1 is signifying. Okay, so if we look at the following reaction of, for example, an alkyl halide with water, we find that the tertiary alkyl halide reacts faster than the secondary, which reacts substantially faster than the primary. So this clearly is not an Sn2 reaction. Clearly, we're looking at an entirely different mechanism here. Because the pattern of reactivity based on substitution is clearly quite different. It's the exact opposite for that matter. Okay, so let's try to figure out why that is. And let's try to look a little bit at the mechanism. So the mechanism for the Sn2 reaction occurs in two discrete steps. First, we have our loss of leaving group. And this is the rate limiting step. This is the slowest step in the process. Now, once we have our carbocation intermediate, in our second step, we have the attack of our nucleophile. Okay. And then typically you have to do a cleanup step where you either deprotonate your product just to generate your neutral species. So to look at another example of like a classic Sn2 mechanism, for example, if we have the following species, so if we have, for example, the following if we have the following alkyl iodide and we treat it with in a solution of methanol, and we heat it, we can likely observe some Sn1 reactivity. So in our first step, we lose our leaving group, that's step 1. We end up generating a carbocation intermediate. Now, since this carbocation intermediate is planar, we can observe approach from either the top or bottom face. So the product stereochemistry, or the product stereochemistry, is a mixture. Of stereoisomers. So in the Sn1 reaction, compared to the Sn2 reaction, we observe a mixture of product stereochemistries. We observe a mixture of diastereomers, as the planar carbocation can be attacked from either the top or the bottom face. And as a result, we get a mixture. Does everyone understand, and does it make sense to everyone, this idea that because we're going through a carbocation intermediate, inherently we're going to observe a mixture of product stereochemistries? Does that make sense to everyone? Does that idea make sense? Because the carbocation's flat, we can approach and attack from either face. That's why we observe a mixture of product stereochemistries. Now, it's really important in your mechanisms that you show the cleanup step where you deprotonate your product or you remove any highly acidic protons. So that way you can report your final neutral products. I know it seems like just extra work, but it's really important because the actual products that you isolate in the majority of cases are going to be neutral. Okay. So here's an example of a fully drawn out Sn1 reaction mechanism. We have our rate limiting step, which is the loss of our leaving group. Once we lose our leaving group, we generate a carbocation. The carbocation can be attacked from either face. That's why we observe a mixture of diastereomers for our product. Does that make sense? So let's unpack this Sn1 reaction a little bit further, and let's practice the mechanism for the Sn1 reaction. So let's look at the following substrate, and I'd like us to draw out a full and complete mechanism for this reaction. So let's take about 3 minutes to work through this example. And then I'd like students ideally to share their responses either as a photo in the chat or using the annotate tool. And let's try to get a few responses for this reaction mechanism. And I'd like you to indicate the product stereochemistry. Do we observe a single stereochemical outcome? Do we see a mixture? What do we see? So let's keep working on this example, and really don't be shy to share your proposed responses in the chat, verbally, as a picture, and don't be shy to ask a question in the chat or verbally. Would anyone like to break out the annotate tool and try to share their responses? You can access this under the meeting controls option. I just want to make sure everyone's comfortable with these examples. And for mechanisms, the only real way to do that is to make sure students are comfortable drawing out the mechanism. You can also, if you'd like, you can talk through the steps and I'd be happy to transcribe your proposal. Okay, so let's see. So we have a student saying the sulfur attacks from the top or bottom. What's the first step? What's the first step in the SN1 reaction? What's the first step and the rate limiting step? Yep, so we have the loss of our leaving group and we generate a carbocation. So the first step, our leaving group leaves and we make a carbocation. Okay, then in the second step, you are correct in noting that sulfur can attack from either face, the top or the bottom. And as a result, we end up generating, well, we would generate a mixture of diastereomers. This molecule is symmetrical, but it's always important to note that the SN1 reaction occurs with a mixture of products. We end up with a mixture of diastereomers. Now, are we finished here? Is this the last step? Can we call it a day at this point? Is this the same product as indicated when we're asked to write a mechanism? Is this the correct product? So the hydrogen, yes, we do have to get rid of the hydrogen, and this is an acidic proton. So we have a basic species floating around. So rather than the hydrogen just leaving, can we draw out a proton transfer? Can we draw out a proton transfer? Can we draw out a mechanism similar to a typical acid-base reaction to remove this hydrogen, to remove this proton? What does everyone think? Can we transfer this proton to our nucleophile? Can we transfer this proton? Something like this. Which of these two mechanisms is preferred? The one on the right or the one on the left? Does hydrogen just leave, or do we pull off our proton? The mechanism on the right, exactly. We're removing our proton via an acid-base reaction or a proton transfer reaction. Perfect. Okay, so in the end, we end up generating our mixture of products. And in this case, these two products are identical. But that's not always the case. Key takeaways: Sn1 reaction, two-step reaction going through a carbocationic intermediate. Second important point to consider: the Sn1 reaction occurs with generating a mixture of diastereomers for your product, because you can attack the carbocation from either the top or bottom face. Barring anchiomeric assistance, you'll get almost a racemic mixture, or almost a one-to-one mixture of diastereomers if you have other stereocenters. Does this example make sense to everyone? Okay, so let's keep going now, and let's look at the Sn1 energy diagram. Okay, so as we can immediately see, it occurs in two discrete steps. So we have our first step here, which is the loss of leaving group. And just looking at this energy diagram, if we compare the first step, which is loss of leaving group, to the second step, which is the attack of our nucleophile, my question to all of you is, which step has the larger activation energy and which step is rate limiting? The first or the second step? The first step. And that makes sense intuitively, right? Obviously, it's pretty difficult to make a carbocation. Carbocations aren't particularly stable. They're pretty high energy species. So it takes a large activation barrier to generate our carbocation from our starting materials. Okay, now let's also pay attention to the energetics of this process. Is the first step exergonic or endergonic? So the first step, is it exergonic or endergonic? Endergonic. Okay, why am I bringing this up? Why am I bringing this up? So an endergonic reaction, the transition state resembles the species, the species are intermediate closest in energy, which would be our carbocation intermediate. So our transition state energy is going to be heavily influenced by the energy of our carbocation intermediate. Our transition state will resemble a carbocation intermediate. And as a result, and this is really important, we can use the same principles in terms of carbocation stability that we've talked about when we looked at, for example, alkene substitution, electrophilic reaction, or electrophilic substitution of alkenes. All of those patterns of reactivity based on carbocation intermediates, we can apply just as easily to the Sn1 reaction. Okay, so with that established, let's talk about this reaction in more detail. The rate determining step is slow formation of the carbocation. The fast step is our carbocation being immediately trapped by the nucleophile. Now, The rate law for an SN1 reaction solely depends on substrate. It's a first order reaction that only depends on the concentration of alkyl halide and is independent of the nucleophile. So when you think SN1 reaction, I just like you to think this idea that the nucleophile is not very important. Any nucleophile will do, even pretty bad nucleophiles for the SN1 reaction. Okay, so the stereochemical outcome for the SN1 reaction, there's not too much to say in this matter. The intermediate SN1 carbocation is planar and sp2 hybridized, and it's achiral. The carbocation can react equally from either side. I'm just going to put a little asterisk barring substrate effects. And the product is racemic or has a very, very, very minor amount of inversion. And this is based on this idea of contact ion pairs. For practically, you observe just a racemic mixture because your nucleophile can attack from either face of your carbocation. Does the stereochemical outcome for the SN1 reaction make sense? Does everyone see why we get a racemate? Perfect. Okay. So just as a side note, for the racemate and the inversion process, the carbocation is slightly biased to react on the side opposite to the leaving group. This is because the carbocation is loosely associated with the leaving group, shielding one side of the carbocation via contact ion pair. So you do observe a small preference for inversion. Practically, this isn't very useful. Okay, let's talk about the characteristics of the SN1 reaction. The SN1 reaction proceeds through rate-limited formation of the carbocation. This is a unimolecular process. The rate increases with increased stability of the carbocation. So this is based on this idea that any factor that stabilizes a high energy intermediate stabilizes the transition state leading to that intermediate. So remember, our transition state resembles the carbocation intermediate. So if we have a very low energy carbocation, the resulting transition state will be lower in energy, and as a result, the activation barrier will be lower. So that's why we see a general trend where we have tertiary reacting faster than secondary, which is about equal to benzylic and allylic. In general, if you have a stabilized carbocation, it will react quite efficiently via an SN1 reaction. Does that idea make sense? Does this idea make sense? The rate of SN1 reaction is directly related to the stability of the carbocation generated from primary, secondary, tertiary, allylic, and benzylic substrates. Is everyone comfortable with that idea? Okay. So, in terms of electrophiles in the Sn1 reaction, the methyl and primary electrophiles do not favor formation of stable carbocations, and as a result, they're not useful for Sn1 reactions unless they're a resonance stabilized carbocation. So just like the Sn2 reaction, you don't see an Sn2 reaction with a tertiary substrate. You will functionally never see an Sn1 reaction with a primary substrate that's not allylic, benzylic, or resonance stabilized in some manner. Does that make sense to everyone? Okay. So to elaborate a little bit on why allylic and benzylic halides are particularly reactive and why they can present a very interesting issue, allylic and benzylic intermediates are stabilized by the delocalization of our cationic charge. So when you have an allylic halide, you can observe a mixture of regioisomers, right? Because you have a mixture of potential carbons that have cationic character. So your nucleophile can go in and attack at both of these cationic sites, and as a result, you observe a mixture of regioisomers. Does that make sense? So fundamentally, the Sn1 reaction occurs with the attack on our carbocationic carbon, right? And if we have our charge delocalized over multiple atoms, you may see a mixture of regioisomers. Now, another thing that I'd like you to note, primary allylic and benzylic substrates are reactive in the Sn2 as well as the Sn1 reaction mechanism. And this is where we're going to start to see the impact of solvent and reaction conditions on the mechanism. Nucleophile and solvent control will dictate whether you see primarily Sn2 or Sn1 reactivity. So we'll talk a lot about that later on in the chapter. Okay, so let's talk a little bit about the effect of leaving group. So the Sn1 reaction is very leaving group dependent. Would someone like to provide a guess or a reason why the Sn1 reaction is particularly sensitive to the leaving group? What's so special about the Sn1 reaction? What is our rate limiting step? What is the rate limiting step? This is a hint. What is the rate limiting step? Formation of the carbocation, yes, via loss of leaving group, right? So in general, the better our leaving group, the faster the rate of Sn1 reaction. So good leaving groups are generally weak nucleophiles, or they're considered weak bases or large atoms that can readily stabilize electron density, right? Additionally, positively charged atoms generally make good leaving groups. You can see our table of leaving groups that we presented earlier on in this chapter. Some sample good leaving groups would be your halides, your mesyl and tosyl groups, acetate, water, and alcohols. So good leaving groups are very beneficial for an Sn1 reaction because they accelerate and they make the rate limiting step easier to accomplish. Now, oftentimes the Sn1 reaction can be run under Bronsted acidic conditions. In this case, leaving groups can be activated via protonation. So if we compare our leaving group, initially we have a leaving group of hydroxide. Is hydroxide a good leaving group? In general, is hydroxide a good leaving group? hydroxide with this. Yeah, it's not very good. So it's not a good leaving group. However, if we protonate it, now we have our leaving group as water. Is water a reasonable leaving group? Is water a really bad nucleophile and a really sort of a really bad base? Yeah, it's not very good at all. So water is a great leaving group. So running reactions under Bronsted acidic conditions can activate leaving groups and can help accelerate the rate of SN1 reactions, all things being equal. So this is one method of activating your leaving group. The other method, which slightly more sophisticated but works through the same principle, is that coordination of a Lewis acid to a Lewis basic lone pair can activate a leaving group for elimination or activate it for SN1 reaction. Now, this can either be a coordination process or a direct formation of a bond. There are many ways to deal with this, whether you're using a Lewis acid or a formal reactive electrophilic species to activate your leaving group. In either case, it's the same reason why protonating an alcohol activates it as a leaving group. Coordination of a Lewis acid can also activate your alcohol as a leaving group. Does that idea make sense? Does everyone see these two ways that we can activate our leaving group? Via Bronsted mechanisms where we protonate, or via Lewis acid coordination. Okay, perfect. So in terms of the nucleophiles in the SN1 reaction, since the nucleophilic addition occurs after formation of the carbocation, the reaction rate is not normally affected by the nature or concentration of the nucleophile. So you don't see a lot of dependence on the nucleophile, almost functionally no dependence on the nucleophile for the SN1 reaction. Does that make sense? The attack of the carbocation is the fastest step and it's not rate limiting. So you shouldn't see any dependence of the reaction rate on the attack of the carbocation and the nature of our nucleophile. Okay, so let's talk a little bit about examples of the SN1 reaction and some key features of the SN1 reaction. So when we're preparing alkyl halides from alcohols, the reaction of our tertiary alcohol with acid is fast and effective. Primary and secondary alcohols react very slowly. This is a typical SN1 reaction. And as we see, the tertiary substrates react the fastest, followed by the secondary, followed by the primary and the methyl. One thing to note, and this is a good segue into our next topic, elimination can occur at higher temperatures. So let's delve and expand in on that idea, as it's pretty interesting to consider. So to draw a mechanism for this reaction, so if we have our tertiary alcohol and we treat it with hydrochloric acid, so in our first step, we will activate our leaving group. Okay, then we observe the loss of our leaving group and we end up generating our carbocation. This is our rate limiting step. Finally, what is our nucleophile in this process? What is our nucleophile in this process? What is our nucleophile for this SN1 reaction? So we treat this alcohol with hydrochloric acid. What nucleophile is derived from hydrochloric acid? Would anyone like to volunteer a guess? So what nucleophile have we generated from these first two steps? What nucleophile can we attack our carbocation with? We're using hydrochloric acid. So what nucleophile have we generated? Would anyone like to propose the nucleophile that's participating in this reaction in the chat? What nucleophile is being used in this case? Chloride, exactly right. And chloride, of course, can attack from either face. And if this was a stereocenter, we'd see a mixture of stereoisomers. But because this is not a stereocenter, we just install our halide. So this is a useful method of making alkyl chlorides. And these alkyl chlorides can then be derivatized and modified. Of course, we can eliminate them, and we'll see later on conditions to control the elimination process. So, does this example make sense? Does this mechanism for an SN1 reaction make sense?
Yep.
Perfect. Okay, so let's keep going now. And let's talk about the role of the solvent in the SN1 reaction. So solvent effects in the SN1 reaction are largely due to stabilization or destabilization of the transition state. Polar solvents facilitate the formation of the carbocation intermediate, and protic solvents stabilize the transition state. Now, since you're stabilizing your carbocation also stabilizes your associated transition state and increases the rate of carbocation formation. So the SN1 reaction really likes its protic and polar solvents, while the SN2 reaction, just to showcase this comparison, likes aprotic solvents. So does everyone notice a clear difference between the SN1 and SN2 reaction in terms of solvent choice and solvent preference? Okay. Increasing your solvent polarity or utilizing a protic solvent results in a very dramatic increase in reaction rate. So for example, switching from ethanol to water as our solvent results in almost 100,000-fold increase in relative reaction rate. So the more your solvent has a polar and most importantly a protic nature, the faster the rate of SN1 reaction. Does that make sense to everyone? Perfect. So let's talk a little bit about solvent effects in the SN1 reaction. So polar protic solvents stabilize the carbocation-like transition state, resulting in a faster rate of reaction. So if we compared the energy diagrams for aprotic versus protic solvent conditions for the SN1 reaction, we could tell it's an SN1 reaction because we have two unique steps. The protic reaction rate is substantially faster because we have a lower activation energy because we've stabilized our carbocation intermediate and our transition state is lower in energy. Does that idea make sense? You should be able to draw out these energy diagrams. Is everyone comfortable with that idea? Okay. Yes. Did someone have a question? Okay, let's keep moving on then. So let's talk and let's directly compare the Sn1 and Sn2 reactions. In terms of substrates that can easily stabilize a carbocation, so tertiary, allylic, benzylic, prefer to react via Sn1 pathways. While further, hindered substrates prefer to react via Sn1 pathways. In terms of the nucleophile, strong nucleophiles favor the Sn2 reaction. Let me use a different color pen so that way it's easier to tell. Strong nucleophiles favor Sn2 reactions, while weak nucleophiles favor Sn1 reactions. Interestingly, the Sn1 reaction rate is unaffected by nucleophile strength, while the Sn2 reaction rate increases with strong nucleophiles. In terms of solvents, polar aprotic solvents accelerate the Sn2 reaction rate. Conversely, polar protic solvents stabilize the carbocation intermediate, resulting in a faster rate of Sn1 reaction. Do these points make sense to everyone so far? This is just review of all the effects that we've seen so far. We're doing a head-by-head comparison, Sn2 and Sn1. What is different and how do the conditions affect which reaction is preferred? Now, the universal sort of shared beneficial trait of both the Sn1 and Sn2 reactions is that good leaving groups accelerate the rate of reaction. So I've made a table where it can help you think through whether you have an Sn2 or Sn1 reaction. So just to show you how it works, first you consider your substrate. If you have a primary substrate, it's going to be Sn2. If it's a tertiary substrate, Sn1. Overwhelmingly, without a doubt. Now, when you have your secondary hindered allylic and benzylic substrates, these are more ambiguous. And that's where you're going to need to start to look at your nucleophile and solvent, okay? Now, if your nucleophile is strong, well, then you're likely dealing with a Sn2 reaction. If your solvent is aprotic, that's another point for the Sn2 reaction. If you're dealing with a protic solvent and you have a weak nucleophile, you're likely to see Sn1 reactivity patterns. Now, I don't want you to memorize the table. This table is just summarizing all of the ideas that we've talked about so far in these lectures for the Sn1 and Sn2 reaction. Does everyone understand why the table works and how to sort of assess whether you're dealing with an Sn1 or Sn2 reaction? You start with your substrate and then you look at your nucleophile and solvent. Does that make sense?
Yep.
Perfect, perfect. So let's do an example. So we're asked to predict the products of the following reaction. Now, note, when I say predict the products, I need you to specify stereochemistry as well, right? So the only way to answer this question is to first figure out what mechanism we're dealing with. Well, let's start with our solvent, acetonitrile. Is that protic or aprotic? Protic or aprotic? What do we think? Acetonitrile, protic or aprotic? Would anyone like to contribute their proposal? What do we think? Is that a protic or aprotic solvent? Aprotic, exactly right. Okay, so that's 1 point for the Sn2 reaction. Looking at our nucleophile, is that a strong or weak nucleophile? So is this thiol a strong or weak nucleophile? Yep, it's a very strong nucleophile. So that's another point for the Sn2 reaction. And then looking at our substrate, is that primary, secondary, or tertiary? Primary, secondary, or tertiary? What do we think? Is this alkyl halide primary, secondary, or tertiary? It's secondary. So we have a secondary substrate, that's ambiguous, but we have a strong nucleophile and an aprotic solvent. So then this looks like to be an Sn2 reaction mechanism. So then we would draw our mechanism as a concerted single-step process that occurs with inversion of stereochemistry. And as a result, I should clearly indicate that we just have a single stereoisomer. Or at least at the bare minimum, just note that we aren't generating a mixture. Does everyone understand this process? We look at our substrate, we look at our solvent, we look at our nucleophile. We concluded because we have a strong nucleophile and an aprotic solvent, it's reacting via an Sn2 mechanism. Secondary substrates, we can't say much from the substrate perspective. The Sn2 mechanism occurs in a concerted manner with inversion of stereochemistry. So we draw the mechanism in a concerted manner. And our product is generated with inversion of stereochemistry. Does that make sense? Any questions on this example? So this is a good stopping point for today. So what